So I wanted to talk about a ring defined by Lusztig that captures some properties of affine Hecke algebras. The techniques are maybe a little far from the interests of many of the attendees, but there should hopefully be some at least conjectural applications, which are maybe more in the spirit of some of the things we saw earlier today and might see throughout the week. Sort of baby cases, if you take a finite Weyl group. So for example, the symmetric group, this is a Coxeter group. So it has a presentation where it's generated by some involutions that obey some relations like this. And the Hecke algebra of such a thing is a deformation of the group ring. So it's some ring over Laurent polynomials in a formal variable with basis indexed by the Coxeter group we started with, and the following relation. So there's a quadratic relation. So when Q is equal to 1, this just gives you back that the SI are involutions. And when the lengths add, the basis elements multiply in the most natural possible way. And so this is a deformation. So with Q equals 1, you just get back the group ring. In fact, so there are two ways to see this. One, for a finite Weyl group, for a finite group, it's just a theorem that any deformation of the group ring has this property. But in fact, for almost all complex numbers, non-zero complex numbers, this is always going to be the trivial deformation. So this fails to be the trivial deformation except at finitely many roots of unity. And Lusztig defined a ring that actually implements this independence in an explicit way. So what does that mean is that there's a base ring called J, which is defined over Z, so no formal variables, with basis also indexed by the Weyl group, equipped with a map from the Hecke algebra to J with extended scalars, which at all but these finitely many roots of unity specializes to an isomorphism. So not only are these deformations almost always trivial, but in fact, they're isomorphic to this explicit ring, which is defined over Z. So the easiest example, a symmetric group of order 2. In this case, the Hecke algebra is two-dimensional. There are two elements, two Kazhdan-Lusztig basis elements. And on those Kazhdan-Lusztig basis elements, Lustig's map is given like this. And it's pretty easy to see that this is an isomorphism whenever Q is not equal to -1. So in fact, what Lusztig showed is that his map, this Lusztig phi map, extends to an isomorphism when you take function fields. It is sufficient to invert a single polynomial, in fact, which is the Poincare polynomial of W. So this is some polynomial of this form where the EI are the exponents of the Weyl group in question. So for the symmetric group, it's just like 1 through n-1. You also get this number when you count points on flag varieties and so on. So the main point is that for finite Weyl groups, there is an algebra that implements this independence in Q. To get this independence, it's sufficient to invert a single polynomial. So in particular, it's an isomorphism away from this roots of the polynomial, which can be seen to all be roots of unity. If you go instead to affine Weyl groups, then you can define the affine Hecke algebra in the same way. It's the same deformation with the same relations. And there is again a ring J. There's again an asymptotic Hecke algebra. And in this case, you can't quite just take function fields, but you should take the following very mild completion. So you allow infinite sums of Kazhdan-Lusztig basis elements and infinite sums of basis elements of J. And you allow formal Laurent series coefficients, which converge in the sort of Q inverse adic topology. So a pretty mild completion, and Lustig's map is again an isomorphism. In this case, there are sort of two potential ways that if you look at the preimage of an element of J, it's sort of infinite in two different ways. So it's an infinite sum of elements in the affine Hecke algebra, and the coefficients are Laurent series instead of a priori instead of rational. So the main result I wanted to talk about is that the second potential infinity doesn't actually appear. So this is an infinite sum of Kazhdan-Lusztig basis elements, and it's an infinite linear combination. But in fact, the coefficients are rational, and they have poles only at a finite set of roots of unity. And that set depends only on W tilde. Only finitely many roots of unity appear for any basis elements. Moreover, I'll say in a minute that there's a combinatorially important partition of the affine Weyl group. And the denominators of these rational functions depend only on these, this partition. They depend only on the two-sided cell containing the element W. So the proof is actually via harmonic analysis on p-adic groups, as you might guess from the title. An example for, say, p-adic SL2, the affine Weyl group is just the infinite dihedral group. And what do these elements of J look like? Well, they look like infinite linear combinations like this. So in particular, the coefficients are rational functions, and the denominators are all the same. For elements that aren't the identity, if you take a reduced expression for some y in the affine Weyl group and look at the subwords that you get by just only including the first k simple reflections, you get a formula like this for the preimage of this element under Lusztig's map. So the interesting thing here is it's written in the Kazhdan-Lusztig basis, and it turns out that the coefficients in this case are polynomials. So in this example, the only way you get rational functions even is by summing this very simple geometric series of terms. So how to do this in a little more detail? So if you pick some connected reductive group over a p-adic field and its dual group over C, then you get a root datum for G, and you can define the extended affine Weyl group as the semi-direct product of W and the co-weight lattice of the p-adic group you started with. So W here is the finite Weyl group. This is not in general a Coxeter group. It has a bunch of elements of length 0, but it does have a length function, and it is generated by simple reflections, and it is tame in the sense of such groups, and you can apply all the constructions that Lusztig did for finite Weyl groups. He was able to pretty much immediately apply for these extended affine Weyl groups. Affine Hecke algebra has the same presentation as for finite groups. You again have the Kazhdan-Lusztig basis of the affine Hecke algebra, and you have its structure constants, which are some Laurent polynomials in q to the 1/2. There is a function, this Lusztig A function, whose value on z is minimal, such that q to the a z over 2 times any structure constant for z is a polynomial in q to the 1/2. So whatever x and y you start with, if you get z out of their product, multiplying by q to the a over 2 will kill all the negative powers. So for example, for simple reflections, this thing is equal to 1. And you can make a pre-order on the affine Hecke algebra by saying an element is less on the left than another element if you can make it by multiplying against y on the left, and cx occurs in this. And you can make equivalence classes, and these are the left cells of the affine Weyl group. And likewise, you can do this for the two-sided cells. So everything you can get by multiplying on the left and the right against some fixed element is less than in this pre-order. So the left and two-sided cells, as well as the right cells with the obvious definition, partition the affine Weyl group and show up frequently in the combinatorics of Coxeter groups. So they're counted by, well, it's actually not completely, it's known how to count two-sided cells. The number of left cells is actually complicated, and I think not in general known. So there's a finite set of involutions inside the affine Weyl group, such that each left cell contains exactly one of them. Lusztig calls these the distinguished involutions. And hence there are finitely many two-sided cells and finitely many one-sided cells. The A function is actually constant on two-sided cells, and kind of, it doesn't separate them, but it knows about them to some extent. So the way you define this J ring is by defining these integers to be the constant term of these polynomials you get from the structure constants of HF. So example of distinguished involutions. And this is basically all you can get. You can get the identity, simple reflections, and like longest words in parabolic subgroup. The theorem of Lusztig is that these integers gamma, x, y, z actually obey the right properties to define an associative product. And the identity in J is kind of strange looking. It's the sum over all the distinguished involutions. So this is a finite sum. And the various TDs are actually orthogonal idempotent. Ring J is a direct sum of the corresponding two-sided ideals indexed by the two-sided cells. So for example, the affine Hecke algebra is filtered by ideals that have something to do with two-sided cells. And this thing kind of rigidifies that into being an honest direct sum. So then the last sort of major definition we need is Lusztig's homomorphism is defined using the structure constants from multiplying against distinguished involutions. And you kind of throw away everything that doesn't land in the same A value as your distinguished involution. So this is injective, and its specialization is injective for all non-zero complex numbers. So what is this ring good for? The representation theory of the affine Hecke algebra is described completely by Kazhdan Lusztig and is pretty much independent of Q. So this knows about a large subcategory of representations of the corresponding p-adic group, which in general depend heavily on Q, but this part sort of doesn't feel Q at all whenever Q is not a root of unity. And in fact, for harmonic analysis, Q can be any strictly positive real number. Algebra J kind of implements this independence in the sense that if you know how the Kazhdan-Lusztig classification works, simple modules over J are indexed by exactly the same triples, exactly the same sort of Langlands parameters as simple representations of the affine Hecke algebra. So a unipotent element in the complex dual group, a commuting semi-simple element, and a representation of some finite group, their centralizer. The point is that not only, I mean, you can prove this classification and kind of see that it really doesn't depend on Q. For example, Q does not appear in the triples, but you can also sort of implement that independence by saying, here is this other algebra defined over J, over Z, that kind of manifestly has nothing to do with Q. So how to introduce the tools of harmonic analysis? If F is our p-adic field and G is connected reductive over F, and crucially F split, then if B is a Borel and A is the maximal torus in B, I is the Iwahori subgroup corresponding to B. The Iwahori Hecke algebra is the convolution algebra of Iwahori bi-invariant functions on the p-adic group. It's a classical theorem of Iwahori and Matsumoto that this thing is just the specialization of the affine Hecke algebra when the formal variable kind of underlying Q to the 1/2 is the square root of the prime power that's the size of the residue field. And the isomorphism just sends one of these standard basis elements to the indicator function of the corresponding double coset. And like I said, this algebra knows something about representations of the p-adic group. It's equivalent to the category of admissible representations with Iwahori fixed vector. If you have such a function, it acts by this, it's possible to make sense of this vector valued integral, and that defines the module structure. A representation is tempered if all its matrix coefficients lie kind of almost in L2 of G mod the center. These are the types of representations that you can study with harmonic. They're constructed very briefly. If you take a Levy subgroup of your p-adic group, a representation whose matrix coefficients, representation of M whose matrix coefficients legitimately lie in L2 of M, and a unitary unramified character of M, then all the tempered irreducible representations of G are parabolic inductions of such twists. All be realized on a vector space that doesn't depend on the character. Hence, the tempered representations are parameterized essentially by a disjoint union of unit circles, of compact tori. And it makes sense to talk about how they depend on the character and how endomorphisms of them depend on the character. Just like the affine Hecke algebra was modules over that were equivalent to sort of a big category of representations, the tempered representations are also modules over some algebra, some sort of analytically defined algebra. You can ask, because the space that they're realized on is independent of the character, you can ask how you can characterize various functions based on how regular their Fourier transforms are in the character. So the Iwahori-Hecke algebra corresponds to endomorphisms of tempered representations that are algebraic in the character, and the whole Schwarz algebra in things that are smooth in the character. So just matrices whose entries are algebraic functions or smooth functions of the character. The theorem that powers this is a description due to Braverman-Kazhdan of the ring J in terms of p-adic groups. So namely, if you have a tempered representation, the Iwahori-Hecke algebra action extends uniquely to a J action, preserving irreps. And this defines a map from J to the Schwarz algebra. And in particular, elements of J kind of go to things that are rational in the character. So sort of the point is that you're trying to make J into an algebraic version of the Schwarz algebra. And you do this by saying what kind of endomorphisms J acts by, how they depend on the character. So we want to study J via this map to the Schwarz space. So recalling that you can write the preimage under phi as such an infinite linear combination, but in fact, this perspective doesn't really appear much in Lusztig's work on J. He has a complete classification of its representations, but it doesn't use this fact. So in light of Braverman-Kazhdan, you can ask, well, what do these coefficients look like? Are they rational functions? How do they converge? What do the poles look like if they're rational functions? Do they satisfy any kind of positivity property? And if these converge when specialized at a certain prime power, they define a function on the group. We know that there's a Schwarz function associated. The group, what is the relationship between these two? So there's a Schwarz function associated by Braverman-Kazhdan, and how do these relate? So the conjecture is that these coefficients are rational functions of the formal variable, just like in the finite case. The denominator doesn't depend on x, but only on the two-sided cell containing w. There is some natural number such that a power of the Poincare polynomial of the finite group clears all denominators of these coefficients. Same is true for formal degrees of square integrable representations of all the levies, but that's sort of a minor thing. The main result is that if W tilde is the affine Weyl group of GLN or SP4, then this conjecture is true, and the Braverman-Kazhdan map is injective. In general, it can still prove that they're rational functions with denominator independent of x and depending only on this two-sided cell. And there is some kind of polynomial that clears denominators, but for the moment, I can't prove that it's the Poincare polynomial. But for a certain two-sided cell, it's possible to see that it is still. Again, these things have poles only at a finite set of roots of unity. And again, this Braverman-Kazhdan map is injective. So like I sort of said already, in the SL2 case, you can rewrite things so that there's a certain positivity property in the coefficients. This suggests some kind of categorification in terms of constructible sheaves, but for the moment, there's neither such a categorification, nor can I prove a positivity property like this in higher rank. Interests of time, I'll probably skip the idea of the proof, but the point is to use the Plancherel formula. And how does that appear? So the point is that if you have any Schwarz function, you can recover it from the endomorphisms it gives. Namely, its value at 1 is the integral of its trace over all tempered representation. What does this look like in practice? Well, from the construction I mentioned, it's some sum over Levy subgroups of some integral over the characters of the Levy, the unramified unitary characters of that Levy. So example for GL2, when the Levy subgroup is just the torus, the diagonal torus, unramified characters look like this. The simple tempered representations are just the irreducible unitary principal series. And this integral is just an integral over two copies of the unit circle of this rational function. So for example, in some cases, we can show the trace is just 1. And in that case, you can really just evaluate this integral using the residue theorem. And you get, in this case, the same denominator as we saw before. So in particular, it's possible to prove the trace is always a regular function of the zi's, independent of q. So the only poles you pick up come from this rational function that already appears in the Plancherel formula. In the last few minutes, I want to mention a potential or a sort of conjectural application. So the original proof of the Kazhdan-Lusztig classification of representations of the affine Hecke algebra requires that Q is not a root of unity. They have a geometric construction, and sometimes a variety they need can actually be empty if Q is a root of unity. She proved about 25 years after Kazhdan-Lusztig that in fact their classification holds everywhere except roots of the Poincare polynomial of the finite Weyl group. So in fact, this can only fail at finitely many roots of unity. And earlier, she had computed that for a certain two-sided cell, so the two-sided cells are in bijection by theorem of Lusztig with unipotent conjugacy classes in the dual group. The conjugacy class of the identity is a very special two-sided cell for which these things are normally proven first. And there, the Kazhdan-Lusztig classification fails. I mentioned how this classification works, but essentially all the standard modules for that unipotent you can build, their simple subquotients kind of sit in the wrong level or the wrong degree. You don't get any simple modules associated with the unipotent 1. The main result shows that denominators that you get such an expression depend actually only on the two-sided cell. Every two-sided, for whatever one of these Schwartz functions associated to a basis element of J you get, when you put it into the Plancherel formula, it only feels one Levy depending on the two-sided cell. And because the traces are regular, the only way you get denominators, period, is from the form of the Plancherel formula for that Levy. So in particular, all the denominators you get only feel the two-sided cell. And so the poles they can have are actually attached not to the element, but to the two-sided cell. And so this gives a notion of how singular in Q each two-sided cell of the affine Weyl group is. And the big cell for which there's this counterexample is actually the most singular in Q. So its denominators are the entire Poincare polynomial, and definitely you can't make sense of this when Q is a root of that. But there are cells that are less singular in Q. And the conjecture I'm going to conclude with is that if you have a two-sided cell and it doesn't have a pole at Q in the sense of the asymptotic Hecke algebra, then the Kazhdan-Lusztig classification should work at that unipotent. So namely, for every standard module, there's some geometric construction of these, has a unique simple quotient, and the A value of this simple quotient, which I haven't defined, but is required to make this classification sort of non-degenerate, is equal to the A value of the corresponding simple module over J, which is how this classification is supposed to work. So the idea is that you should be able to do some computations, you should be able to do some integral, and the integral should tell you whether or not the Kazhdan-Lusztig classification will work for that particular root of unity. So that's all I wanted to say.